ready to get started here. My name is Rodney Daughtrey. I'm from ITA Software in Cambridge, Massachusetts. And today I'm going to be talking about ITA software and orbits and some work that we've done building a search engine and list. So this is just sort of a brief outline of what I'm going to be going over today. I'm going to give some background on the online travel industry, ITA and orbits as companies, and then sort of a mini tutorial on the airline industry and what it means to do low-fare search. And after that, we'll examine some list-related issues with respect to the search engine that we've written in Lisp. I'll sort of briefly touch on some interesting problems that we've had in user interface design for air travel, and then take any questions if there's any time. So this is sort of the big picture of air travel planning. Let's suppose that I want to take a trip to San Francisco on October 26th, like I did in Michigan, and return to Boston on October 30th. Well, I'm probably going to call up an airline agent or a travel agent, or perhaps I'll visit a travel website or an airline website, and I'll ask them, I'll give them a query to say, I want to go to these places during with a particular set of times. Now, these agents actually don't have the ability to answer this question. They have to pass the query on to a search engine. And search engine is written by a handful of companies in the world. ITA Software is one of them. Sabre is another one. There are 4 or 5 others. And they attempt to answer the query that's posed, given information about the flights, what flights are flying to what places, prices in terms of what fares can be used to cover those flights, and also seat availability, what seats are available on what planes at the current moment. Just a little bit about online travel. Travel is what people spend the most money on the web. The online travel sites took in about $20 billion in 2001, which is about 36% of all U.S. e-commerce. And that's expected to more than triple by 2007. Nearly 50% of all, well, nearly 43% of web servers access a travel site each month, and currently approximately 10% of travel reservations are made online, which might seem a little low to you, but the remaining 90% of the world still makes reservations through travel agents or by calling airlines directly. So just a little bit about ITA Software. We were founded in 1993 in Cambridge, Massachusetts by Jeremy Wertheimer, who was a student at the MIT AI lab. This was kind of a thesis avoidance project for him. And between 1996 and 1999, we developed a core search engine, starting really with first principles. And that was really developed by the first 10 employees. About 7 of those were Lisp hackers. The primary author was Carl Markin. You probably heard Peter Norvig mention him earlier. In 1999, November, we launched www.itasoftware.com, which is our website. It's mostly a showcase for our technology. We don't actually make money on our website. It has about 1 million users, strictly through word of mouth. We haven't done any advertising or anything like that. Today we have 50 employees, 5 customers, including Orbitz, America West, and some others. So just a little bit about Orbitz. Orbitz is owned by a consortium of United States or U.S. airlines, and including most of the major carriers in the United States. They launched in June 2001 using our search engine for domestic travel, not for international travel. We're still working on our international product, which we hope to announce pretty soon. Orbitz did about 12 million unique visitors in January 2002, and they were selling about 30 to 60,000 tickets a day about a year ago at this time. I don't have the numbers for their current traffic. They were doing about 1 million low-fare searches a day last year at this time. They currently sell about 2% of the airline tickets in the United States. And we provide Orbitz with new software releases about 4 times a year. And that's bug fixes, new functionality, things like that. Okay, so I'm going to give you some background on some low-fare search concepts and just sort of the airline industry in general. Part of low-fare search is generating itineraries, which will get the user to where they want to go. And what you're looking at here is a picture produced by the itinerary generator of our search engine of the 2,000 quickest paths for the outbound portion of the trip that I took out here to San Francisco a few days ago. Now, some of the arcs on this graph that you see represent multiple flights between the same airports. So, for example, there is only one arc from San Francisco to Chicago, although it might be hard to see in there. And that just represents all the flights on different carriers that would actually go between those two cities. There are some interesting things to note about this graph. All the paths that you see might actually be reasonable for some travelers. They're reasonably direct. Most are in the United States, some in southern Canada. All of them are length 3 or less, so that's up to 2 stops, which some people might consider. And all of them depart and arrive the same day. But that really doesn't really begin to exhaust the possibilities. That's just the 2,000 quickest. Here are the 10,000 quickest paths. These are all still arriving on the same day. And a few more airports actually come into consideration. But again, no path is really out of the realm of possibility. So, some things to note. This is just for Boston and San Francisco. For a round trip, of course, you have 10,000 ways back to Boston. So, if you're looking at a round trip, for example, the trip that I came out here on, that's 100 million possible flight combinations. It's also important to note here that the number of paths grows exponentially with the length of the trip. So, for example, San Francisco to Paris, which would probably might be 4 or 5 legs for the cheapest answers potentially, is much worse. So, that might be billions or trillions or even worse numbers for the number of possible flight paths. So when I first came to ITA, I thought this is what our search engine spent its time doing. Trying to figure out the possible ways of getting from here to there, but I was wrong. So it turns out almost all the difficulty in travel planning and low-fare search comes from prices and not flight paths. So just a few definitions here. The atomic unit of price in the airline industry is called a fare. And a fare is the price for one-way travel between 2 cities, which is called a market. So, for example, Boston to San Francisco would be called a market. And a fare has rules restricting its use. So, when you can use the fare, who can use the fare, and these kinds of things. So there are a few axioms, and enjoy these because these are probably some of the only rules that aren't violated in the airline industry, for which there aren't exceptions for. And these are things like each flight must be covered or paid for by exactly one fare. But a single fare may actually pay for more than one flight. You can use multiple fares to pay for all the flights in a journey. So, for example, I'll get on to that in a minute. And another definition is something called a fare component. This is one of the sort of prime definitions in the airline industry, which refers to a fare and the flights that it covers. Now, here's an example of that. Suppose we have the following flights in blue: San Francisco to Boston, and then Boston connecting in Dallas-Fort Worth and going back to San Francisco. And we have 3 American Airlines fares. One possible way that you could cover the flights with these fares is to just use the Y fare. These fares can often be used in the reverse direction from what they're filed. So, for example, the Boston to San Francisco fare can be used to cover travel San Francisco to Boston most of the time, according to some rules. So, in this particular case, we have 2 fare components, and the second fare component is sort of an interesting one that covers, that has one fare covering 2 segments: Boston, DFW, and DFW to San Francisco. And you just, in this case, you simply add them together to get the price. So, 1,000 plus 1,000 is $2,000. So here's another possible way you could fare this particular set of flights, just using the other 2 fares in the American set, the 3 fares that American has for Boston, or the other 2 fares in this table, just using the Boston DFW fare and then the DFW to San Francisco fare. So these are just possible ways that fare components can cover flights. Now, the next concept is something called a priceable unit. Now, the way to think about this is fare components can be thought of as sort of atoms. And a priceable unit is a molecule. So fare components can combine to form priceable units, but only in sort of a set of several fixed geometries. And a ticket is finally built from a set of priceable units. So just a side note, priceable units are sort of the domain for which many fare rules apply. For example, the Saturday night stay is a priceable unit level sort of restriction. Priceable units are sort of one of the evil things of air travel pricing. They're responsible for most of the difficulty in pricing air travel. So here's just some possible ways that you could break fare components and use fare components and priceable units up to cover a set of flights. And you can sort of see the different, the red arcs are fare components, and the yellow shapes are the priceable units. So for the example here, we have 4 flights shown and 6 possibilities for how it could be covered, but there are many more than this. Just a little more background about the airline industry. Airlines publish sets of fares at different prices in each market. And often there are many, many fares for a particular market. In this example, we have British Airways, who has 280 different fares from Boston to London. Some airlines actually publish as many as 1,000 fares in some markets. And there are sort of these industry extensions, sort of macro systems, for example, something called constructed fares, which can sort of double or triple that number. So anyway, just sort of in summary about fares, each fare has a different price and this sort of different code, this fare basis code thing that was on this previous slide. Let's see. For example, the Y, QD14, and K21AP there. And a potentially different set of rules governing its application to any particular set of flights. Okay, this is hopefully the last slide on the airline industry pricing. Here are just some sort of sample fare rules that you might see on a particular fare. A rule that says that the first flight in the fare component must depart on a Tuesday or Wednesday if you use this fare. Surcharges that say add $22.50 if you're going to Boston to San Francisco. this is a fuel surcharge in this particular case, or add $20 if you're going San Francisco to Boston. And actually the reason for that is the prevailing winds, and apparently it's cheaper to go one way or the other or something, than use less fuel. Things like the 14-day advance purchase, Saturday night stays, things you're probably familiar with. Combinability is another type of rule, back-to-back rules, and many, many more. To sort of, oh yes, and one thing, if you see to the right of this, the rightmost table, you see a routing. Fares often have a routing associated with them, which is essentially a directed graph of permitted routes within the fare component here. And in this particular example, the routing says that the fare permits nonstop travel, say, between Boston and San Francisco, which is the line going all the way around on the right side, the arc on the right side. But it also, this fare can also be used if you stop in New York City, Chicago, DFW, and LA, but not DFW and Chicago. So, we have to sort of deal with these routings and make sure that we don't apply fares that can't be applied depending on the flight path that you're taking and these types of things. Kind of an interesting side note. Notice that the price is the same in this case. You can use this fare whether the traveler takes one flight, the Boston to San Francisco nonstop, or four, the New York City, Chicago, DFW, and LAX route. And which is interesting because those are wildly different costs to the airline. And in some case, it's even anti-correlated in the case where in many cases cheap fares prohibit nonstop travel for a lot of popular business routes. So in that case, the airline's prices and expenses are anti-correlated, which is kind of a strange thing. Anyway, to top all this off, the fare rules are expressed in extremely complicated language invented 35 years ago by a company, well, I'll leave it at that. So, why is airline pricing so complicated? Why do we have this mess? It's really because the airlines are they're trying to maximize profit. They want to fill the plane with as many business travelers as they can get, paying $1,000, $2,000 a seat, and then filling the rest of the seats with leisure travelers, paying whatever they can get from them. Because one of the first rules of airline economics is you don't want to have a plane take off with any empty seats, because that's just lost revenue. You should have charged the person a quarter, or whatever, gotten some money for that seat as opposed to none. Actually, it's not quite true. Probably the cutoff is somewhere around $30 because of baggage handling and things of those nature. But anyway, this desire to want to maximize profit and get as much money for business travelers as opposed to or getting $2,000 a seat for business travelers and then getting whatever leisure travelers will give you raises a big dilemma, because now how can you possibly justify selling the exact same thing, a seat on a plane, for vastly different prices to these two demographic groups? And the answer is, well, how can we do this? Well, we'll invent some arbitrary rules called Saturday night stay, advance purchase. Now, the airlines really don't care if you buy your ticket 14 days in advance or 21 days in advance. I mean, it's not like they need to get ready for it. This is just a way to segment the two demographic groups so that they can get away with doing this. And it's interesting, the graph on the left here actually shows a claim that the airlines often make, that there is no single price that they can actually charge, the blue horizontal line on this graph, and still make money. They maintain that they need this distribution of prices to survive. So, with business travelers at the high end. And whether or not this is true is, it's certainly debatable, but it's interesting. Okay, so now I'm going to sort of switch over to the algorithm that we have for dealing with this stuff. This is vastly simplified, but it's really enough to sort of get the idea of how this works. The first thing that we really do is the first slide that I showed you with the paths between how to get from here to there. We generate possible solution paths from the passenger requested origins and destinations, subject to the given airline flight schedules, of course, and also subject to seat availability. So early on, we check to see if we don't want to generate solutions on flights that don't have any seats available, because we won't be able to use those later. And then the second step of the algorithm really is to sort of overlay the fares on these solution paths, according to all the fare rules and restrictions and constraints between the fares, the fare components, the priceable units, and so forth. And this is where we've spent the last 6 years of our lives, really, is doing this kind of thing. This is really about 75% of the programming effort. So after we sort of overlay the fares on top of the flights, we do this using a factored graph representation. And so we construct a graph of possible solutions. And often the graph represents, for complex trips, up to 10 to the 20th solutions that you can enumerate from the graph. And then we enumerate some solutions from the graph according to a particular evaluation function, or value function, in terms of do you want to see the cheapest particular solution, do you want to see the most convenient solution, and so forth. Kind of an interesting side note is that our search engine is definitely computation bound. It's really not database bound. A very small portion of the time that you do your orbits and are sitting there waiting for the query to come back is spent computing. It's not spent accessing data. That's a very small portion of our query time. So just very briefly, here's some numbers on the data that you need to do low fare search and how big they are and things like that, and how often they change. Flight schedules are typically around 700 megabytes of data. They don't change very often at all. The airline fares, depending on whether we're working with a domestic low fare search system or international low fare search system, is pretty different. For international, it's around 2.4 gigabytes of data. And that changes about 3 to 5 times a day. These first two types of data, flight schedule and airline fares, we can essentially get away with not using a database for these things. We just memory map them on the servers that do on the same machine that the low fare search server is running on. Now, seat availability is a slightly different situation because this changes continuously, every second. And for that, we built a separate system that our search engines consult at the time that it's generating itineraries in the search. And that basically asks, the search engine actually asks seat availability queries of a cache that we built, and this cache is sort of a separate system that all it does all day long is query the clearinghouses, for example, Sabre, and ask availability questions of every flight leaving in the United States for the next month or something. Just a little bit about what it takes to run an ITA search engine. You need the fastest PC you can find. We run under Red Hat Linux. It requires about 1.25 gig for domestic low-fare search and 4 for international. And a common configuration that people run at least the domestic low-fare search engines in is they have a single machine which has dual processors, and then they'll run 2 servers on that particular machine, both accessing the same data on that machine. Okay, let's talk about Lisp. So we've written our search engine completely in Common Lisp, except for the data management portion, which is done using C data structures, and then we access the C data structures via fixed num pointers in Lisp. There are 253,000 lines of code. It's been written over, I guess, about a 6-year period. The code's migrated over four Common Lisp implementations over that time. We're currently running on Allegro Common Lisp and CMUCL. We don't allow garbage collection, and I'll talk about this in a minute. We basically do all the memory allocation stuff ourselves. And it's highly optimized for speed. It's very important for our system to be as fast as possible. It's a situation where, while the query is running, people are literally waiting on the other end for it to finish. So speed is important to people like Orbitz. So why does ITA use Lisp? Well, this was an interesting question. I talked to Carl about this quite a bit. And the thing that we sort of came up with was it's probably because the primary reason is algorithmic complexity. The algorithms that we're using to do this kind of stuff are pretty complicated, and probably more than anything, more important than anything, is just that we can see through to these algorithms as well, as we can. And Lisp sort of provides that better than any other language that we know. So, just trying to see through to the algorithms themselves. And another advantage is that it's really great that the Lisp data structures sort of remain resident after a query executes, because we spend a lot of time debugging queries that complete, with no errors or something, but that actually produce buggy answers. So we'll go into the data structures after the query completes and say, okay, why didn't we get this, fair? Or why did we get this fair? That type of thing. This is no surprise. Incremental compilation in the development environment. This is just huge. When making any change to the data management C++ code means a recompile of all that code, and it's a lot of code and it takes a long time. Whenever we change a C function, we have to unmap all the data, all the fair data, which is a whole lot of data. And it's sort of our general practice, and this sort of goes back to something that Peter Norvig said earlier, I think. Basically that if the code changes a lot, we want to keep it in Lisp. And if it doesn't change a lot, then maybe we can afford to move it to C for various reasons. But if we're going to be changing the code a lot, we keep it in Lisp because it's just so much faster and easier to change than the C code. Again, large chunks of code are often rewritten due to the airline industry, constant change in the airline industry. We use macros for building languages, sort of internal languages that can reason about fare components and priceable units and these airline industry types of things. And then less important, but certainly nice, is the ability to sort of hot patch, running production servers with incrementally compiled patches and things like that. So what downsides have we had with Lisp? Well, probably the biggest issue that we've had is address space. We've had to move our static data structures out of Lisp and into C. We sort of keep running into the 32-bit process limit, the 4 gigabyte process limit, and we just haven't had a lot of luck with the Lisp garbage collectors in Lisp images that are just really big. Another big area is performance. One thing that we had some trouble with is we've often just been able to often been unable to optimize critical sections of code when we look at the disassembled Lisp code and it's inefficient. We've also had to write quite a few of our own versions of a lot of sort of basic common Lisp functions for things like sorting and sequence operations, just so that they're fast enough and so that they don't dump cons and things like that. And just in general, many of the existing libraries are not sort of sufficiently optimized for performance requirements. So just a little bit about the no garbage collection requirement. We basically do pools of resources that pre-instantiated data structures and sort of resource pools of con cells and these types of things, so that are pre-allocated, so that we just use those and we don't ever create new structures on the fly. We simply, at the beginning of a query, will clear these structures and then populate them in the process of doing query. And then, yeah, as I said before, garbage collection of just Lisp images as large as 1.5 or 2 gigabytes are just we've had some problems there. So sort of query input and output is pretty simple. As you might expect, we use XML for both input and output. The XML input query is translated to an internal format. Before we had an XML interface to our search engine, we had sort of an ITA internal API for things, and so the XML layer sort of maps to that ITA internal input layer. On the output side, we write XML directly from Lisp using sort of this XML generation ecology stuff that we've written. And again, this is kind of a homegrown XML solution that we sort of had to come up with based on the fact that it had to be fast and didn't cons and things. So now I just want to briefly touch on some what I think are kind of interesting problems with UI design for a search engine like this, or sort of UI design for air travel in general. So when we started, I guess about 4 years ago, just like with low-fare search, we sort of started from first principles on what kind of user interface you would need to sort of present results. And we did a lot of usability testing, and we actually used CLA-CDP for dynamically generating the web pages. And the UI design that we came up with was sort of co-opted by Orbitz for their own website. There are some interesting challenges coming up with a UI for this kind of stuff. One that we didn't really appreciate up front was just the fact that the solution space of answers, when you get back the answers to this low-fare search query you get, are just completely illogical on many dimensions, or on the dimensions with respect to cost. So, it was kind of interesting. For example, Peter Norvig mentioned in his talk that a UI with sliders with just preferences and things like that. We actually tried a version of that, and this sort of non-smooth solution space just made that a complete nightmare, because you would do things like, we had a slider for convenience. You would tweak the slider and say, okay, I want a little more convenience. And the price would go from $600 to $200. You'd be like, okay, maybe a little more, back to $2,000. How about a little more convenience? Down to $150. How about a little more convenience? Down up to $700. It made absolutely no sense. And so, we quickly threw that UI out. So that was kind of an interesting, problem in that how do you present a space that makes absolutely no sense from a pricing perspective to the users? So that was one big challenge. Another one was that we have 10 of the 12 answers. Which ones does the user want to see? A good example here is that the first 1 million cheapest answers for a query are often virtually identical. So, for example, on the trip, coming out here, I don't know, some large number of the top solutions, maybe near a million, were America West, leaving at 6:15 a.m., connecting in Las Vegas, and connecting with 30 other airlines at many other times a day, fared, with 100 different fairings over each one of those. So, and that was the top solution. So, if you don't want to go on America West, or you don't want to leave at 6:15 a.m., or you don't want to go to Las Vegas, you probably want some other solution than one at the top of it. So, that was kind of a problem also. And just sort of the general UI desirable list. You want it to be easy to use, you want it to be powerful, responsive to the different criteria that are important to each user. So we really started from, we sat down and just asked, what do we think people care about when they plan a trip? And we came up with a laundry list. And this is sort of, what you might think would be on the laundry list. But after we made this laundry list and sort of started asking people and playing around with this, we sort of made two important realizations. And that's that different people really do care about different criteria than on this list. So, for some people, cost is definitely the most important thing. Other people, number of stops or duration, lower convenience. For some people, they have proven flyers on some carriers, so that's what they care about. Some people say, well, just definitely, I'll take any solution that flies into Manchester, New Hampshire, or some people say, I don't care as long as I'm not on the problem, et cetera, et cetera. So that was one important thing. If you ask 10 people what they care about, you get 10 different answers. So that sort of poses a problem for what kind of solutions to present. It's also another important realization was that it is a low barrier search site. So presumably people care about cost. That's why they're there. At least one of the reasons that they're there. So we found that people definitely want to trade off price against the other criteria that they care about. So we started playing around with different UI ideas, and we essentially came up with something we call overview tables, which it's a pretty simple concept. It's just a simple table format that allows two criteria to be examined at once. One along the horizontal axis, one along the vertical axis. And the third criteria, price, or the criteria of price, appears in the cells of every table. And then we simply selected the tables that we thought were the most useful criteria pairs that people cared about. So here's a picture of what you get if you do a search on our website and the search results. The top section of the screen there is what we call an overview table. And it sort of serves two purposes. Number one, it sort of gives you a big picture of, okay, here are, in this particular case, this is all the carriers across the top that could service the query that you ask about against the number of stops down on the vertical axis. And the prices in the interior cells reflect the lowest price for that number of stops and that carrier that you could possibly get, or that our surgeons came up with, I should say. And it also serves as sort of a launching point to zoom into solution subspaces that hopefully are relevant to the user. So, maybe they say, okay, I just want to see all the delta nonstop solutions. And you can, click on that link, and then those solutions are displayed below. So again, here's the airline by number of stops table that we came up with. It answers some fairly relevant questions, I think, for what people might want to know: what carriers offer the lowest price, what airlines service the trip, what airlines offer nonstop service. What's the trade-off of taking a nonstop versus a one-stop, and things like that. Here's another table which just plots outbound versus return flight times, and then gives you the lowest price for each of the time bins. So this, for example, lets you answer questions like, when is the cheapest time that I can go, or depart or arrive? What are the possibilities? In this particular case, I can see that I can't depart, midnight to 6 a.m., which doesn't break my heart in this particular case. But, another type of table plots outbound versus return airports. So this answers the question of how much does it cost to depart from Boston as opposed to Manchester or Providence? How much does it cost to arrive in Oakland as opposed to Sacramento, San Francisco, San Jose, things like that. So Orbitz decided to use this, but they only decided to sort of use a subset of the table idea. They just used one table, which is the default table on our side as well, the carrier by number of stops table. So just in closing, I wanted to say something about Lisp. So I sort of thought hard about what our future with Lisp might be. And I think Lisp is nearly essential for us. And but it's definitely the case that its obscurity is causing us some pain. And a lot of this is what Peter Norvig referred to in our previous talk. Just sort of, the numbers of programmers, Lisp programmers versus, other languages just means that some of the libraries, often aren't there, or things of this nature. And just the fact that we don't have many vendors in the space, and they all have limited resources too, and it's hard for them to get everything done that people would like to see. But anyway, even though there are problems, we're probably not moving away from Lisp anytime soon. And the main reason for this is the algorithm clarity. I should probably put that bullet a little higher on this list. That's probably the main reason for us, is that we have to be able to modify this code as the airline industry changes. And it's much more difficult to do that if the code is in C, or if it's in some language where we literally can't see the algorithms. And it's also just much easier and faster for us to write code in Lisp. Customers certainly don't care that this stuff is in Lisp, because we have XML input and output APIs. So they're just sending XML to us, and we're sending XML back. So they don't care what language it's written in. And that's pretty much it. Questions?
Do you have any plans to contribute the speed estimate back to CMUCL?
Yes, we do. We have a really good guy, Martin Krakauer. Do you know Martin? And I'm sure that he's going to commit those back to CMUCL.
Thank you.
Other questions?
Time for one more.
One more?
these port systemization, you're still using ACL and CMUCL. Can you talk a little bit about the nature of this there and why you couldn't do this implementation?
Well, I mean, one definite reason for using two list implementations is that ensures that you're not going to do something that sort of stupidly ties you to one. That's one reason for using two. Just like having code on Red Hat Linux and also having code on HUX.
You have production code, run on two, or you just file it?
Currently, we don't have production code